Swayam Prabha. Digital India. Educated India.
Okay, very good morning, and we had a very long day yesterday. We had sessions in the morning and afternoon. So, just one thing I want to mention about before we move on to the other topic. So, today I think one of the participants was asking this point. She was noticing very nicely that if you look at the two boiling regimes, we have the nucleate boiling dominant and convective boiling dominant. If you look at a given section or location along the tube, you will find that the bubbly flow regime is much longer in the nucleate boiling dominant, whereas in convective boiling it is very short and then immediately it goes to slug flow and then annular flow, and that is what is basically the advantage of using a convective boiling. At the same time, there are, if you look at the quality of vapor, the vapor quality will be higher in the convective boiling dominant case, somewhere exactly at the same location. So, if I draw a location, a line like this, my vapor quality X will be higher in the convective boiling compared to the nucleate boiling, right. But then the question that she was asking is, if that is the case, how does the critical heat flux get enhanced when I increase my mass flux? As it goes more and more towards the convective boiling dominant, how does the critical flux get enhanced if my vapor quality seems to be higher? So, the answer is, in nucleate boiling, if you look at the heat transfer coefficient, so it peaks when there is a bubbly flow regime, right, and as the bubbles coalesce and then they become larger and what we call a slug flow, slowly the heat transfer coefficient reduces. Okay, the power of nucleate boiling is when absolutely there is no movement of the fluid and only nucleation is happening. But in convective boiling it is the other way. You see the heat transfer coefficient peaks at a point where the quality of vapor is high, So, this is what is shown in this particular graph here. Heat transfer coefficient is plotted as a function of quality, and for the nucleate boiling, obviously when the vapor quality is very less, that is the maximum heat transfer coefficient, and then as the vapor quality increases it drops, because that is how the thing, it reaches a critical heat flux and after that it becomes very bad. So, it has to continuously drop here, whereas with convective boiling you see at a quality of around 0.8 is where it peaks. So, that means that this is actually in the slug and annular flow regime is where the maximum heat transfer coefficient for convective boiling dominant happens. So, it is not like simply if you compare, of course, the vapor quality 1:1, the vapor quality seems higher in the convective boiling dominant, but because of the convection it is continuously feeding in a pool of liquid. So, that liquid film surrounding the slugs is continuously replenished. So, it does not dry out or does not reach the critical heat flux as quickly as we think. So, by increasing the supply of the liquid, so even if the vapor quality is high, so you are continuously replenishing the liquid film, and once you are in the slug flow and annular flow regime is where the power of convective boiling is, because as you see the higher the quality, the maximum the heat transfer coefficient in the convective boiling. So, that is what happens. So, if you look at this figure, intuitively you will think that convective boiling is going to dry out faster, right, because the vapor quality is high, but that is not the case, because as you keep increasing your mass flux, as the liquid film is getting replenished, you will see that the critical heat flux is also getting progressively higher. So, that is the advantage of combining convection along with the nucleate boiling. So, in flow boiling, when you are basically operating with using both the power of nucleate boiling plus adding convection, so that the convection is going to cause the early merger of all these bubbles, and this will progress very quickly to the slug flow regime, and not only that, it is also continuously feeding the liquid film surrounding the slugs. So, that is more important as far as the enhancement in heat transfer is concerned. Okay. So, that is why why should we go to flow boiling, and what is the advantage of combining nucleate and convective boiling is the main question I think she was asking, and I hope that is also clear, because I think many of you probably did not look at this very closely yesterday. So, now we will move on to another topic which is on the measurement techniques for multiphase heat transfer, because some of you are already doing experiments in your research and then you want to understand what are the necessary techniques that we can use, especially in multiphase flows. So, we have of course done some measurements ourselves. So, based on that I can talk about a few of these techniques here. So, I mean, as you all know, so why do accurate measurements matter, so whether it is measuring multiphase heat transfer or single phase heat transfer, one thing with phase change heat transfer like boiling, condensation and evaporation is the experiments to capture this phenomena is more difficult. So, for example, when you want to set up pool boiling facility, okay, so you can measure, of course with thermocouples you can measure the surface temperature of the heater, the fluid temperature, and if you have an arrangement where you can visualize it with a transparent enclosure, you can also visualize how these different regimes of boiling is happening, the nucleation and then transition and so on. But then if you want to have a surface and you want to study, for example the heater surface, how the distribution of temperature is and things like that, then simply using thermocouples may not be adequate. So, then you have to use some non-invasive techniques like infrared thermography and so on. So, for temperature measurements which are non-contact, non-invasive, so using infrared thermography is one of the state of the art techniques that people have been trying out. And why do we need such kind of measurement? So, if you were talking about say doing a velocity measurement using PIV, or looking at temperature distribution using infrared imaging, so all this information that you get from experiments, finally you have to also use numerical models to validate with these experiments and build numerical models. For example, the confidence in numerical modeling of multiphase flows is still very low. Even if you look at simple multiphase flows without heat transfer, people are still working on developing advanced numerical methods, and now when you talk about phase change like boiling and condensation, we do not have very reliable numerical models. So, in that case, how do you validate these numerical models with the measurements that you have? So, you should have good quality measurements first, so that you can have a reliable set of data to validate your numerical method. So, that numerical methods are also having some confidence, and you can develop these numerical models in a more advanced manner. So, that is the main purpose. I think we are going to focus on these measurement techniques, and just to give a overall categorization. So, we can broadly categorize measurement techniques as invasive versus non-invasive. So, what are these invasive techniques? As you all know, if I want to measure, for example, the pressure or velocity, I use a pitot probe or a hot wire. So, I have to put a probe exactly at the point where I am going to measure this property, and when I put the probe is not just going to be a passive sensor, it is also going to actively disrupt the flow. So, therefore, there is an invasion or intrusion of this particular probe into my measurement quantity, and therefore, this itself might alter the measurement values. Okay. And on top of that, if I have surfaces on which I do some measurement, and if there are some particles like solid particles and so on moving at high velocity, you can even damage the probe. So, for example, you have a hot wire probe, these are very thin films, you have hot wire films which are of the order of microns, and if the flow by itself you are putting air flow or water flow which has lot of dust particles and so on, they can actually damage your probe sensor. So, all these issues are there with invasive. Number one, they are not going to give you an accurate representation, they are also going to disturb or distort the flow. And second is there is also a chance that these probes can be also damaged due to interference by these foreign elements in the flow. So, but the advantage is most of them are relatively low cost. So, you can usually afford them to buy it in your lab. So, some of these techniques for velocity measurement, for example, pitot tube, you have used hot wire anemometer or any optical probes. For example, you can connect it with a microscope if you want to watch a very small region where bubbles are nucleating and things like that. But I think most of you must have handled pitot tubes for measuring pressure and velocity, and a few of you have also used hot wire anemometer, which is a very standard technique for measuring velocities. Of course, all components of velocities can be measured with the hot wire anemometer, and it is also very accurate for measuring turbulent flows. Now, what about temperature measurement techniques? So, we use standard thermocouples, and these thermocouples have to be calibrated. That is very important, because the accuracy of the temperature data that you get depends on the accuracy of the thermocouples that you are using, and these thermocouples have to be calibrated with some industrial standard calibration units that are available, and sometimes people also use RTDs for very fast transient response and so on. And of course, thermocouples are broadly thermocouple, but all thermocouples are not the same. If you need a fast response, you need to measure quantities of the order of micron scale. If you are using microchannel, for example, you may need a faster response, you may need micro thermocouples. Okay. So, therefore, thermocouples are also coming with different tags and categories, and you have to be aware what your interest in measurement is. Now, when we talk about non-invasive techniques, as the name suggests, obviously they are completely non-invasive. You do not have to put these probes directly into the path of the flow or somewhere. So, they do not disturb the flow field. However, they are very expensive naturally. You have to invest a lot of money to purchase a very good infrared camera or a very good PIV system, right, because hot wire you can buy it for maybe 10 lakhs if you buy a Dantec in a single component hot wire probe, but if you are investing in PIV, it may cost at least 40 or 50 lakhs to get a 2D or 3D PIV. And again, non-invasive techniques also need proper calibration. So, if you use infrared camera, so you are picking up emissions not only from the surface which you want to measure, but also from the surroundings, from the air or wherever you put it. So, you have to know exactly how to calibrate it for the system, so that the temperature that you detect with the camera is exactly the surface temperature and not having any noise. Okay. So, proper calibration is required even with the PIV systems also. So, velocity measurement techniques include PIV. Okay. Of course, PIV involves high speed imaging, because you need a high speed camera to complete a PIV system, and to measure the, for example, in sprays. So, you have Professor Markov was talking about spray yesterday, and you have when you talk about these kind of sprays coming from atomizers or nozzles. Okay, now you have different planes along the length of the spray, along the nozzle length, and you want to measure what is the droplets size distribution and droplet velocity distribution at each plane, because this is very important to characterize the type of nozzle. So, different nozzles under different flow rate conditions can produce different quality of sprays. So, if you want to assess the quality of sprays, you need to first look at from the high speed image, you need to assess what is the spray cone angle. That is the basic information that you get. So, how much the angle is. So, that will decide what is the quality of the substrate that you are going to cool and what should be the dimensions of that. Apart from that, at each plane like this, so you have a certain distribution of the droplets. The droplets are not always uniform. Okay. There is always a Gaussian distribution that you can make. There are droplets which are of very large size which are there are droplets which are very small size, and then there are droplets along the median. So, all this has to be captured. So, there is a technique by which we use phase Doppler particle analyzer. So, this is basically passing a laser beam as a sheet at each plane, and by means of interferometric techniques. So, it is going to scatter these droplets are going to scatter the laser beam, and from the extent of scattering and from the Doppler shift, from the difference in the frequency, you can actually get both information about the diameter of the droplets as well as the frequency of droplets. So, this is a very advanced technique, especially used for droplet size characterization, but if you just want to measure only the flow field, then PIV itself is good enough. And coming to temperature measurement techniques, the most important thing that you need is an infrared camera if you want to measure temperature in a non-invasive method. So, we will talk about, I think, infrared camera to begin with before we get into the other techniques. So, what is infrared thermography? So, basically infrared thermography is just a detector which is going to detect the emission, the electromagnetic emission coming in the infrared bandwidth. So, basically this is, we all know that when we are trying to get emission from any body, that emission is related to the thermal radiation that is emitted by the body. And what is thermal radiation? It is an electromagnetic radiation, right. So, it is produced due to the thermal motion of the particles in a matter. So, imagine that you have matter at 0 Kelvin. So, you have say molecules like this. Now, if the temperature is slightly above 0 Kelvin due to Brownian motion and so on and so forth. So, even if you look at gas molecules, there is a lot of motion of this, and these motion can actually create charged particles or ions, and the vibration of these charged particles basically emit electromagnetic radiation. So, this is what we call as thermal radiation. So, any object which is above 0 Kelvin has inherently this kind of process where these electrons and so on, the charged particles are accumulated, and the vibration of these charged particles result in the electromagnetic waves. So, the infrared detector is nothing but it is detecting this electromagnetic waves, particularly in the infrared bandwidth. Of course, this electromagnetic band is a very wide band. So, if you look at the entire electromagnetic spectrum, it spans at a very small wavelength, gamma rays, to a very large wavelength which is radio waves. So, you see we have several orders of magnitude variation in the wavelength. So, we have for example of the order of few nanometers on this side, and we have 100 meters on the other side. So, it is a huge bandwidth, and what we are talking about as thermal radiation is usually part of the solar spectrum. So, where part of the UV spectrum is covered, and then it covers the visible wavelength and to a great extent the infrared band. Okay. So, generally from 0.1 micrometer to 100 micrometer is considered the bandwidth of thermal radiation. So, why should we consider only this as thermal radiation? Everything is electromagnetic waves, of course, and it is not like microwaves also produce heat. So, when we do that in an oven, but the reason is it is more related to the solar spectrum. So, if you look at solar black body spectrum, you see that most of it is basically in the infrared region, some portion is in the visible and a little portion in the UV. So, therefore, for us people sitting on earth, our primary source of electromagnetic radiation is from the sun. Okay. And since we are correlating the energy spectrum of the sun with most of the processes that we have on earth. So, it is more appropriate to use the bandwidth corresponding to the emission from the sun as the reference. So, that is why we use this band from 0.1 micron to 100 micron as the thermal radiation bandwidth. Is that clear? Okay. Now, out of which the infrared band is also considerably very big band. So, it is ranging all the way from say 0.7 micron. So, 0.4 to 0.7 is 400 to 700 nanometers is all visible. So, it is a very very tiny part of the entire electromagnetic spectrum, and I mean one of the things, if you look at the Planck's black body distribution curve, is for the sun at approximately say 5000 Kelvin, you will see that the maximum emission of radiation intensity peaks at this wavelength of 0.6 micrometer. So, that shows that why people are probably this could explain why the human eye is probably designed in such a way that we can see only visible wavelength, because that is the wavelength where the solar emissions peaks basically, and not we do not have UV vision or infrared vision, right. So, but if you want to basically detect the emission coming from objects which are at a lower temperature, which are not a temperature of 1000 Kelvin, but of the order of say 300, 400 Kelvin and so on, the peak of this black body emission happens in the infrared regime. So, therefore, you need an infrared camera if you want to detect the emission, maximum emission that is coming from objects which are at slightly lower temperature. Okay. So, that is the advantage of using the infrared, and infrared also has a very wide bandwidth. It starts from 0.7 micron all the way up to 100 micron is generally what we use in most of these cameras. And again infrared has multiple configurations. You can see that there is a shortwave infrared which is very close to the visible part of the spectrum, okay, which is ranging up to 3 micrometers, and then we have the midwave infrared, okay, which is of the order of 3 to 5 micrometer. Now you see this is a graph which shows the transmission of the atmosphere to infrared. Now obviously when you are buying an infrared camera, the camera has to detect the emission coming from an object through the atmosphere, okay, you are not operating this in vacuum, right. So it has to have a window, a transparent window of operation, so that at this wavelength the atmosphere completely has to let the emission pass through, otherwise most of it is actually blocked and you will not get the maximum emission. See, we look for all these atmospheric windows when we design these infrared detectors. For example, you look at the transmission of the atmosphere should be as high as possible. So, if you look at the midwave IR cameras, they are usually operating to detect infrared signals in the range of 3 to 5 micrometer, because that is where you see the atmosphere has a open window for infrared in that bandwidth. So, of course, if you go to 6 or 7 micrometer, hardly atmosphere is not letting anything to come through. So, the detector will not be able to capture anything. So, we work with these detectors which can operate in these transmissive windows. Similarly, a detector operating with the long wave IR can be designed to operate from anywhere from 8 to 12 microns. So, this is also another window where the atmospheric transmissivity is quite high, and therefore, most of these detectors are designed in such a way that they operate within this particular midwave IR or long wave IR. Okay. So, as I said, thermal imaging camera works by detecting and measuring the infrared radiation that is basically emitted from a particular object. So, it is basically capturing the emission, it is not capturing some reflected light like your optical cameras. So, your optical high speed cameras or whatever you have, it is based on principle of reflected light that is captured, but infrared cameras detectors capture exactly the emission that is coming from a surface. So, you think most of you probably know about the surge in infrared cameras during the COVID time, when most of the airports and other places, screening centers, they were using IR cameras extensively to detect people had a temperature, fever and so on, right. So, therefore, for scientific purposes, of course, people have been using infrared cameras for research, and so the invention was actually contributed to a Hungarian physicist in the year 1929, who invented the IR camera as a night vision camera, and that the invention was nothing to do with scientific research, but it was for surveillance, for military surveillance, before the World War II had happened. So, of course, but later on people started using this for also research purpose, and you have now different types of cameras which are operating in these bandwidths. As I said, you have a shortwave IR camera. For example, FLIR is one of the major companies which manufactures these infrared cameras. It is a global leader, and if you visit anybody who is having an IR camera in a research lab, usually they will be having this FLIR, and we also have a couple of these FLIR cameras. For example, the one that is shown here, FLIR A655SC, is a long wave IR camera that we have. So, it detects the infrared emission, particularly in the long wave bandwidth from 8 to 12 microns. Okay. So, as I said that this is a band where the atmospheric transmission is very high for the infrared, and therefore, these detectors are tuned to operate particularly in that bandwidth. Oh, that is a big mosquito. My God. Okay. So, you have a midwave IR camera, which also we have X6981SC. This is a high speed infrared camera that we have in our lab, and this works in the detector which is operating in the midwave infrared region. So, like that, depending on the application that you want. So, scientific applications, you can use mostly some of the scientific applications which involve heat transfer measurements use the midwave IR or the long wave IR. Shortwave IR is generally not used, it is more like a black and white image of what you see with your naked eye, you know. So, the objects that you see with a black and white representation, except they are used for probably putting in you know, outside locations where there is a smog and things like that to penetrate the smog. I think these shortwave IR cameras are good enough, but not for detecting the emissions. So, the emission detection is mostly done by the midwave IR and long wave IR. The shortwave IR is going to usually capture some portion of the visible light as well as some of the IR that is coming through from the open environment. So, as I said, the shortwave camera IR camera operates from 1 to 2.5 micron. So, they are usually capturing the light reflected or absorbed by an object. So, it is not exactly the emission that is captured by these cameras. So, they are not very preferred for scientific purposes. So, they are used actually to see through fog, clouds, pollution and like that. For example, this is probably the San Francisco bridge, you know. So, on a foggy day in a visible camera you do not see anything, but once you install a shortwave IR camera, it penetrates to the fog and you can actually see the bridge. So, this is more like a black and white image of your visible camera, it looks very close to that, and it is also used for doing quality control and for even identifying fake currencies, you know. So, people try to see, you know, fake currency by looking at different parameters and so on, but apart from that you can also use a shortwave IR camera to detect that, and you can also detect, for example, some defects in fruits. And so, people who are working in these export of you know, these fruits, they also use these shortwave IR cameras to detect if there are any flaws in these or bruises in these you know, fruits and vegetables. And again you can see this picture where you have a visible camera. So, you have a smoke, the environment is smoky and you are not able to see the background very clearly, and once you install a shortwave IR camera, it penetrates to the smoke and you can see the objects, the buildings and so on quite clear. So, the shortwave IR camera relies on particular sensor technologies, most of these are semiconductor sensors. Okay. So, it uses, for example, indium allium arsenide, you have indium gallium, sorry, this is not allium, this is indium gallium arsenide, germanium, indium gallium, germanium phosphide. So, these are all semiconductor materials that have been tuned so that they can detect infrared in that particular shortwave bandwidth. So, then we move on to the midwave IR camera, which is now most of the scientific cameras are basically designed to detect, and these cameras operate in a wavelength of 3 to 5 micron, and basically now this is a proper camera which can detect the thermal radiation emitting from a surface. It is not just a reflected light or something, but it is a proper thermal radiation that is emitted from surfaces, and these are very sensitive, very fast transient response. That is why you see the high speed infrared cameras are usually midwave IR cameras, and the example that we have in our lab is this X6981SC, which is a very advanced high speed camera. I think at the full resolution it has a frame rate of 1000 fps, right, and then at lower you know, resolution it can be even going to much higher frame rates, because usually the frame rate is inversely proportional to the resolution. The smaller the resolution of the pixel resolution of the camera, the frame rate shutter speed will be much higher. Okay. And now the thing is, you have to be careful using these cameras. You cannot use them in the outside ambient atmosphere, because the ambient solar radiation can contribute to significant noise. So, these are particularly suited where you have an indoor experimental setup and you want to measure things when there is no direct sunlight exposure to these camera sensors. And again MWIR camera detectors also use certain semiconductor devices like indium antimonide, lead selenide and telluride. So, these are some of the common detectors that people incorporate in this midwave IR sensor. And long wave IR cameras are also used in scientific purpose, they are also used in military purposes for example. So, they are less sensitive to thermal noise in the environment, so they can be also used in outdoors unlike the midwave IR cameras. Okay. And of course, these sensors are actually like what are called as microbolometers, and they are made of vanadium oxide or amorphous silicon. The A655SC that we have is a scientific camera which is detecting in the long wave IR regime, and as you can see, so for example, this is also in a daylight in a forest as a person who is camouflaged behind these bushes, and when you use this long wave IR camera, you can actually see the silhouette of this particular person. So, some of these military operations involve using these kind of long wave IR cameras, surveillance, night surveillance cameras and all that, they operate using the long wave IR. So, the working of the IR cameras, so primarily you have two types of cameras, one is called the uncooled cameras. The long wave IR camera that I was talking about, A655SC is an uncooled camera. So, they are having different types of detectors. So, these are the detectors which are detecting the infrared emission. So, one is a pyroelectric type, the other is bolometer, the other is thermopile, and bolometer is one of the standard sensors that we see in these FLIR cameras. So, these are micro bolometers and so on, and each of these have their own advantages and disadvantages. And once when you go to very high speed fast response cameras, they are all cooled cameras, and cooled cameras are mostly based on semiconductor devices. So, they are different types, they are photovoltaic. So, when light or emission strikes them, they can produce some current, then there are photoconductive principles, then there are photodiodes. So, depending on the different semiconductor principles, so they can be used accordingly, and they have very high sensitivity, fast response, and even a single photon or any of this electromagnetic wave which is falling on this can be enough to give a response. So, they can emit some voltage or current depending on the emission that is falling on the particular sensor. However, so these semiconductor devices can operate only at very low temperatures, so of the order of few tens of Kelvin. So, therefore, the entire detector has to be lodged inside a cryogenic cooling system. So, consisting of either liquid nitrogen most of the time, and then this has to be maintained at very low temperatures. So, you have a cryogenic cooler, cryogenic refrigeration system which is already mounted inside the camera, and your detector is actually cooled at this very low temperatures. So, then only you can operate this camera. So, if the, for example, if the cooling system does not work, then the detector ceases to operate. So, this is basically one disadvantage. So, you have to maintain this very well, you have to make sure that you handle it well, and you should not drop it, because if there is any problem with the cooling system, the entire operation of the detector will be gone. But however, most of the high speed IR cameras, including the midwave IR camera I was showing, is based on the cooled detector principle. I do not know. So, sometimes they do not reveal, because people like FLIR, they have their own patented technology, they do not even talk about how this cryo cooling and all these parameters. If there is any issue problem, you have to send it back to the manufacturer, and he will check it and get it back. Even the type of detectors, they are only mentioning the name of the detector, but they do not give you all the details of how the sensor is designed and so on. So, these are all highly patented, because most of these are used in military applications. So, they do not want us to know all the details of this. So, because the same company FLIR is supplying to the US military, as well as supplying to some R&D unit in India, or let us say somewhere where it could be misused. So, they are very careful about the end user agreement. So, generally they do not give it to defense applications and so on. So, academic institutions they give. So, very protected and patented technology. Yeah. So, it has all the things inside. As I said, if you put it outside in the ambient, the noise is going to be very large, because it is going to detect a lot of solar emission. But if you do it in a closed laboratory condition where you protect from ambient light and you take only measurement of your object of interest, this should be very good. And of course I am sure this is not just a detector. So, the entire camera comes with a detector, it is coming with all the technology which is basically processing the image, it is filtering out all the noise. So, it has a lot of image processing units which are already there, and finally it also gives you a software to connect to your computer, and then you can view what it is showing. So, all this is part of that camera. The camera is not just only a detector there. So, there is a lot of image processing and filtration techniques that are being used. So, generally I mean in my opinion it is very straightforward. If you have applications where you need to capture very fast transients like high speed images, for example you have pool boiling. So, you have this nucleation which is happening at a very fast rate, then you need a high speed IR camera which is usually in the midwave. Okay. There are also some long wave IR cameras, I think they have a very extensive array. If you go to the FLIR website, they give you a very extensive portfolio of their camera products, but I am seeing that most of the high speed cameras which are of all the semiconductor type, they are cooled, they are mostly available in the midwave IR cameras. There are also possibly there are some detectors which are also using for LWIR, but they are probably for military applications. Okay. And if you are using normal IR cameras which are not that expensive but not very fast transient, then you can use the long wave IR cameras like the A655 SE I was showing, like this one. So, it depends on your application. Basically if you are just using an IR camera to just detect a steady state temperature of a surface, then you do not need a high speed one, then you just buy a long wave IR camera like this. But if you need something where you want to capture all this bubble nucleation or maybe heat transfer due to spray impact on a surface, so then you may need a high speed IR camera like the midwave one. Okay. So, there are some parameters of the IR camera that you should know, because when you buy them you will be definitely giving the specifications to the vendor. For example, resolution. So, the resolution tells you how many pixels are basically covering the entire IR detector. So, it is just like any camera resolution. So, if you have the camera sensor or detector, how many pixels are basically making up this entire detector. So, as many pixels are there, the resolution is higher, right. So, if you look at the 6901 SE that we have, the midwave IR camera, the resolution is close to a HD resolution. So, it falls short of 1000 by 1000 pixels, but it is something like 700 by 500. 640 by 512. So, something close to that is the resolution. If you need high speed cameras, generally the resolution will not be very high. If you need a HD resolution of the order of 1000 by 1000 and even more 4K resolution and all that, you will not generally get high speed infrared cameras in that high resolution mode. So, usually they are limited by the resolution. Okay. So, typical resolution of IR cameras come in these modes, and the one that we have is 640 by 480, the high speed IR one, and of course, the maximum that you get is in the HD mode, you do not get something in the 4K mode. And there is an inverse and second important parameter is the frame rate. So, how many number of frames you want to take in a given second. So, it depends on what you are basically imaging. If you are imaging a very high speed event, you want to take as many frames as possible, maybe 1000 frames in a given second to capture the sequence of events very accurately, and you want to report a very high time accurate analysis of this fast transient data. And therefore, frame rate of IR cameras or can be up to 10,000 frames. They may not look as attractive as a normal optical high speed cameras, because optical high speed cameras can go up to few lakh frames per second, at even at full resolution, but at maximum resolution these high speed IR cameras can give only up to 10,000 or 20,000 frames per second. But then these are not exactly operating like an optical camera, because they are not just detecting the reflected light, they have to capture the emitted light and therefore you cannot go to very high frames, because again there is a limitation, at least a few photons it has to pick up, right. If you have a very fast transient response and it cannot detect less than a few photons, So therefore these high speed cameras are used in ballistics, supersonic projectiles, explosives, combustion process. For example, we are using in also R&D involving boiling phenomena and spray cooling, and generally the most famous relation is the frame rate and resolution are inversely proportional. So if you are operating at a low resolution, the frame rate of these cameras are quite high, and if you go to higher and higher resolutions, the frame rate has to be coming down. So generally the manufacturer will give you at a full resolution what is the frame rate. For example, the X6901 SE has a maximum resolution of 640 by 480, and at the maximum resolution the frame rate is 1000 hertz, okay, and at a reduced resolution the frame rate will be much higher. So if you are operating that camera at 160 by 120 resolution, then the frame rate is going to be much higher, you can go up to 10,000 frames per second. And why do you operate at a lower resolution? Typically the entire detector is basically divided into 640 by 480. If you have a smaller field of view, if you are capturing only a very small region, okay, this camera can be put at different focal length and you can adjust your field of view. But if you want a very small field of view, just one single bubble I want to capture, then I am going to operate only a very small portion of this detector. So in that case the resolution that I am using will be much lower than the full resolution of the detector, and consequently I can operate this at much higher frame rates, because the product of this frame rate and resolution is usually a constant because of the so many things. One is how the detector can process all this information and send it to the software. So if you are operating at a low frame rate and high resolution, so it can take that much amount of data from spatially but at a low frame rate, and it can send it to the computer. But if you are doing this at maybe a very high frame rate, then the resolution has to be less, otherwise the data that it handles or processes will not be sufficiently good enough. Okay. So basically these are the two parameters that generally you will be using when deciding a particular IR camera, which is resolution and frame rate. So there is also another measure which you should know for a detector to know about the sensitivity of that detector. So it is called noise equivalent temperature difference, and it measures it is a measure of how well a thermal imaging detector is able to distinguish very small differences in thermal radiation in the image. For example, how do you do that is I will have an isothermal surface which is maintained perfectly isothermal, let us say at 300 Kelvin, and I use this IR camera and I take an image. So now when I process the image, I will be looking at what is the maximum temperature difference that this camera is actually detecting. Okay. So if generally they will be limited by the sensitivity of each pixel may actually slightly be different from the other pixel in terms of how they are picking these images. So if you see that thermal contrast or the temperature difference is more than a certain millikelvin, so they should be of the order of few millikelvins, generally maybe 3 millikelvin, 4 millikelvin. If I have a completely uniform image of 300 Kelvin or a surface which is uniformly isothermal to a very precise value of 300 Kelvin, and I use an IR camera, and now if it is detecting a difference of 0.5 Kelvin, then this has a very large NETD, that means the noise is very large. The noise in terms of temperature difference, so that is what it means. NETD is noise equivalent temperature difference. So what we mean as noise is not the ambient noise, it is the sensitivity of pixels and the difference in the sensitivity of the pixels in picking this temperature difference. So if I have a 300 Kelvin surface, if one pixel on one end is picking 300.2, in the other end it is picking 299.8, so there is a 0.5 Kelvin difference. So that shows that there is a very high noise equivalent temperature difference for this camera. So therefore when you start these experiments, it is always good to check this NETD yourself, because the manufacturer usually prescribes this NETD value as a few millikelvin. So, maybe some 5 millikelvin, 10 millikelvin, but when you do this experiment sometimes you will see that this is much larger. Okay. That is because he would have used this camera in a very ideal environment which is completely insulated from the ambient light, and you would have done in circumstances which you are not achieving in your lab. So, therefore, this small difference will be due to this particular ambient conditions, and when you do it yourself you will find that the NETD is much higher. So, how do you do that? As I said, you basically have a surface at a constant temperature and you say take a series of 300 images. If you coat the surface with black paint, then the emissivity of the surface can be enhanced close to 1, so that the emission can be also improved, the intensity of the emission can be improved, and the standard deviation of the data at each pixel so can be taken from the processed image of the infrared detector, and that can be used to calculate the NETD. Okay. I think we have to move a little faster. So these are some of the camera specifications that we have in our lab. So our lab is called Multiscale Thermal Transport Research Lab, which is MT2RL. So we have both the long wave infrared camera, which is the A655SC, and the high speed camera, which is the X6901. So this is a variant of this, it is X6901SC, which is a cooled camera, and you can see the differences as I was talking about the resolution, and you can see the frequency at this full resolution. So you have 1000 hertz frequency. Frequency is basically the we are talking about the frame rate here. Okay. So there is nothing new jargon there, and it also even the quality of the detectors depend on the temperature range that you want to measure. So for example, if your detector is chosen for this temperature range, you cannot use this detector for higher temperature range. So this is only capable of detecting minus 20 degrees to plus 350 degrees. Yeah, all this is a cryogenically cooled. No, I do not think, because each of these detectors are having a certain operational principle, like a photodiode principle or photoelectric principle. So I am not sure whether at such low temperatures, what happens is very few photons actually are falling, right. So because the intensity of the photons which are falling is directly related to the temperature of the body, and I do not know, because the minimum, I think the temperature range that they come out with is minus 20 or minus 30, you do not see minus 100, minus 200 degrees, but there could be, there could be some cameras, but we are not using that. So we do not directly image fluids which are in the cryogenic temperature, because these cameras are used to image surfaces, and surfaces very hardly you go below minus 20 or minus 30 degrees. Right, in any practical application you do not have surfaces maintained at minus 200 degrees unless there is a very specific application for that. And one thing about the accuracy of these cameras is, there is always a question mark about it. It is not as highly accurate as a thermocouple. So you have to take that point very seriously. The infrared camera is not just going to replace your thermocouple. Thermocouple is always superior in terms of measurement accuracy. For example, thermocouples, you can, if you have very finely calibrated thermocouples, you can achieve detection accuracy of 0.1 degree Celsius. Okay, whereas your IR cameras still have a shortcoming there. It can be as high as 1 degree Celsius or plus or minus 2% of the reading, probably whichever is higher. Okay, and the one way to circumvent this issue is to calibrate your IR camera with a thermocouple, and that is what we do usually in our lab. So you have to take a very high accurate thermocouple which is already calibrated to the order of 0.1 degree C, and you use the IR camera and build a calibration curve of the intensity of emission that you are sensing with the IR camera as a function of the thermocouple values, and then you build a calibration curve yourself. So you are not directly measuring the temperature from the IR, you are only detecting the intensity of the emission and then using your own calibration curve to convert that to temperature. So in the process the accuracy can be a bit higher, it still will not be exactly matching the thermocouple accuracy, but something close to that. So that is what we generally recommend in the for R&D purposes. Okay. So yeah, so these are some of the results that we have done in our lab, where we use this high speed infrared camera for temperature detection. So this is a pool boiling setup that we have. This is a test section, and you have a heater, and we have different types of surfaces here. You can have plain surfaces, we can have mini channel or micro channel surfaces. I think I was showing you some results yesterday under pool boiling, where we have done different types of mini channels surfaces on the effect of pool boiling. And we have a regular optical camera which is watching it from side and from the top actually, and then you have the high speed IR camera watching it from the bottom. So like this, so it is basically capturing what is the surface temperature at the bottom of this heater, because there is going to be some non-uniformity in the temperature distribution, because when you look at this boiling phenomena, as I said, so boiling is a stochastic process, right. So you do not have every time when you do this experiment, you do not get nucleation exactly at the same point unless you doctor this nucleation sites. Okay. But if you take a normal surface and you do this, the nucleation site density will keep changing with every experiment. So somebody was asking, so then what is the reliability in the data of these pool boiling curves? So when different people have done these experiments on pool boiling and they plot these pool boiling curves, the general uncertainty in these curves is plus or minus 30%. So that is the kind of differences that people accept should be there when you are doing experiments in pool boiling. And the reason behind that is partly mainly because of the stochastic nature of the boiling process. Even if I have my own surface, I am conducting my own experiment and I am going to repeat this every day, okay, there is going to be a scatter which can result in plus or minus 20-25% variation. So the surface what I am using today may not give you the same curve tomorrow and so on. So this is because the nature of the surface also can be different. So day one you have a new surface, day 2 the surface can get oxidized. So and once the surface gets oxidized, the roughness of the surface changes, and then the cavities nucleation site densities might change, and therefore every day you may actually get some data which is not exactly the same as what you got previously. So there is always a large scatter in such kind of data, and in our case we wanted to see how the temperature distribution along the foil the heater surface is looking, because of these differences in the nucleation and so on. And so this is how we calibrate. So this is our infrared camera intensity versus the temperature that we use a micro thermocouple basically. So we have a separate calibration test facility where we have an isothermal block like a copper block. So we put a micro thermocouple and then we are getting the data from the infrared image, and then we build this calibration curve for a very wide range of temperature which we are interested. So obviously I am not going to build a calibration curve for the range that the sensor can detect from minus 20 to 300, but the shorter the smaller the range of temperature, the more accurate your calibration curve is going to be, right. And my region of interest is mostly in the pool boiling, so it is going to be definitely above 70 degrees Celsius with water. So this is the range in which we have built it. And then we have it is not just doing a calibration alone which is sufficient. When you get the data from infrared camera, it is a raw data which will give you with some noise, and you have to do some filtration and you have to do some image processing and data smoothing operations, and then finally what you get is like a CFD quality image after you smoothen all these things. So this is very close to what you get from a CFD contour, and this is coming from the infrared image after we do the calibration and convert the intensity to temperature, and finally after we run it through the smoothing process, and this is the final outcome. Okay. So now this shows how we have taken the image the foil bottom surface using the IR camera. We get the temperature field, right, we get the temperature data, and each pixel, as I said, of this camera is detecting a certain value. So pixel wise we get the temperature data, and each pixel we do a energy balance. This is called pixel wise energy balance. We do an energy balance, and from the temperature field we extract the heat flux field. So now this is a very ingenious way of doing heat flux measurement. So, the IR camera is primarily used to detect the temperature, but using our pixel wise energy balance approach, we also convert this temperature data into a heat flux data. So, we get both temperature information and heat flux information simultaneously in one shot with only one image. So, that is basically the one of the advantages of using this infrared camera. So, we do not have to rely on other heat flux sensors or using Fourier's law of conduction to calculate how much heat is going, and the other advantage is this heat flux field is also a local data. So, it is not an average heat flux that we get, but pixel wise heat flux. So, it is a very detailed data. So, it can be used to also detect hotspots. So, wherever you have high heat flux regions, it can be very sensitive to detect that. So, I am not going, we have our publication, I think primarily we have collaboration with TU Darmstadt in Germany. So, where they have started this process and we have been using this extensively. So, yeah, these are some of the details, I am just skipping them, but these are some images from our own processing. So, we have the heater foil temperature which we convert to a heat flux after all this pixel wise energy balance. And then what we do is, it does not stop like this, because if you look at the heater foil is of the order of few microns, and then we have the mini channel or micro channel sitting on top of this foil, right. So, we are actually bonding this foil to the mini channel. This is the heater foil. So, using a high thermal conductivity paste. Okay. So, when we do that, so the image that we get is for the temperature at the back of this heater foil, and when we do the image processing, we convert that to heat flux, and this heat flux is at the back of the foil, but we still do not have an exact idea of what is the temperature at the mini channel surface, because of the contact resistance between the bond and the foil and between the bond and the mini channel surface. So, we do an addition conduction simulation by mapping the temperature field that we get into a 3D conduction modeling, and then by applying the heat flux at the field at the top, and then when we solve this, then we get the exact boiling surface temperature. So, you see that the heater foil temperature is this, and finally when we do the energy balance, convert that into a heat flux field, and then when we do a 3D conduction simulation, we get the accurate estimate of the boiling surface temperature. So, this is all coming from the measurement. So, measurement also has to be now supported with some conduction simulation to complete the picture. So, this is at heat flux of 8 watt per centimeter square, and this is at heat flux of 85 watt per centimeter square. So, we also used infrared imaging for a very interesting experiment where we have evaporation of sessile water drops. So, imagine that I have a water drop like this, I want to study the evaporation of this. And how do you generally study evaporation? We use a normal CCD camera and we look at how the water drop volume shrinks due to evaporation. So, the substrate could be either unheated or heated, but we are only studying the profile of this droplet. Now, the idea that we got is, why not use an infrared camera and capture if there are any convection currents happening due to temperature difference that arise during the evaporation process, because during the evaporation process the temperature inside the drop is not uniform. The substrate temperature is different from the apex of the drop, because the apex is cooling faster. Because of the evaporation, the apex will be usually at a much lower temperature than the substrate, and this temperature difference can result in some kind of micro convection inside these droplets, which could be either buoyancy because of natural convection, or it could be due to Marengo effects, because there is a surface tension induced temperature gradient, introduced surface tension gradient. So, these two can result in distinct convection currents, and luckily when we put this IR camera for a water drop, and water is opaque to IR, so which means that whatever the IR is capturing is exactly at the interface of the water and the air. Okay, it does not penetrate water. But if you use things like alcohol and so on, so they are more transparent to IR, and finally they corrupt the data, because you may be also picking up data from the surface, penetrates through the droplet, and you will pick up the emission from the surface and not from the interface. So, then so we did this at different surface conditions, whether it is a hydrophobic or a super hydrophobic and so on, and very nicely we could see some nice interesting circulation patterns inside the drop that we have captured with the IR camera, and we have correlated the circulation patterns. You can see these small convective cells, these are micro convective cells which are inside at different stages of evaporation that we could capture, and this information was coming purely from IR camera, not from optical images. So later the student also did a micro PIV study of looking at how these currents can be captured using PIV particles, and he could also extract these convective currents through the micro PIV, and we could corroborate with the IR data. Okay, now what we have completed till now is only IR imaging. So we still have PDPA. I am going to go very fast because PDPA is something that is most standard kind of instrument that is available. It is nothing that you have to build anything or you have to sit and calibrate. It is a very commercial instrument. In fact, in IIT Madras there is a PDPA facility in the National Center for Combustion Research, NCCRD, and most of us are using, including Monu, who is doing work on sprays. So PDPA is an optical technique. So the primary use of this is to measure the size distribution and velocity distribution of particles in a spray. So for example, suppose you have a spray nozzle like this, and you have this spray coming, and you have this different spray particles everywhere. So what this does is, so you have a laser source which basically passes a laser sheet like this. It is a converging laser sheet, and then you have some optics which are photo detectors. So these are going to capture the scattered light that is coming from these particles. Okay. So it is only going to capture the scattered light, and then it is going to analyze the shift in the frequency and the phase, and from there it is going to give you information about the droplet size distribution. So this is probably the frequency or probability function, and this is your droplet size, so on the x axis. So this can be maybe some 50 microns resolution up to say 300 microns. Similarly, it is also going to give you a distribution of the velocity of the drops, the frequency distribution function for the velocity of these drops. So essentially, so the Doppler principle is used to detect not only the diameter but also the velocity of these drops. So this is important because you want to characterize the spray. So what do you mean as characterization is you want to measure the droplet size distribution at different locations of the spray cone which is coming, like this plane, this plane, this plane, and so on. So at different planes, and then you want to see how good the mean diameter or the mean velocity of these. So depending on the plane and so on, so it will be able to give you this distribution. And what will you do with this distribution? You calculate what is called as a Sauter mean diameter, which is a kind of a mean diameter that generally is used in spray distribution. It is called D32, and you can use this mean velocity and mean diameter at different planes to understand how the spray characteristics of this nozzle are. So that is the main advantage of using this PDPA, and of course there are equations based on the Doppler principle which can be used to extract the velocity and so on. I will give it to you later to have a look. And then PIV, I think PIV also I think most of you know, because here also we use a laser sheet. We at any plane that you want to measure the velocity, we actually make the laser into a sheet using a mirror, and this sheet is actually illuminating a particular plane. And then how do we use PIV here? We use tracer particles, which are the seeding particles, which are much finer than the normal particles, so that you do not have any inertia due to the seeding particles. So these are of a few microns in size, and when you use these seeding particles, they are actually moving. They are like tracer particles, they move with the flow. So if the flow is like showing some recirculation, the tracer particles also are moving with the flow, so they do not have any inertia. So that is basically the idea. The challenge is when you are adapting this to a very small dimension, and when you do micro PIV in a very small dimension, then you have to have particles which are say micron size channels, and you want to do a PIV there. The particles should be of the order of nanometers, they cannot be microns. and again finding these kind of tracer particles and the optical image processing of these reflection from these micron or nano size particles is a major challenge. But the idea here is quite straightforward. So, we have this laser sheet which is illuminating a plane, and you basically seed this particular plane or the fluid with these fine particles which are the tracer particles, and then the region of light is illuminated with a thin sheet as I told you. Then the images are taken by rapidly pulsing the laser. Now this laser is not just a continuous wave laser, but it is a pulsed laser. So, you basically keep pulsing. So, these are like sheets just going at very fast times, and then you are basically having an imaging optic here, and you have a CCD camera which is a high speed camera which is collecting all these images of these tracer particles. So, along with the flow so it is these tracer particles are moving, and the camera is going to collect the snapshots, very fast rapid snapshots of the entire transient of this entire data. So, now we therefore we capture these image in pairs, and then the idea here is when we extract the velocity data, the thing is you should be able to say that this particular seeding particle, all the seeding particles look identical. So, you want to know the same seeding particle has moved to another location in the next image. So, for this we mathematically calculate the cross correlation function, so that we can identify that this is the correct seeding particle which has moved into this location in the next image. So, we take pairs of images and then we build this cross correlation function, and depending on the value you know that this is the same data tracer which has moved, and from the displacement you know the time difference, and you can calculate the velocity of the seeding particle. So, the assumption here is the velocity of the seeding particle is the same as the flow velocity, because there is hardly any inertia due to this seeding particles. So, the major components of the PIV is you need a very good laser light source. So, usually we use ND-arc lasers, okay, and tracer particles must be able to follow the fluid motion with minimal inertia. Then you need a very good digital imaging system like a CCD camera or a CMOS camera, which is a high speed camera, and then you have to do all this post processing. That means you capture all these images, you do the cross correlation function, and then you do the data analysis, and then you calculate the velocity distribution. So, the velocity is simply delta x by delta t. That is a very simple formula, but all the image processing is required basically to come to this stage. Okay. I think we will take a break. So, there is a very short lecture on the contact angle measurement, which I will briefly discuss before we go into the next lecture on thermal management.